The name of this video is Self Inductance. Self-inductance usually happens when we have a single conductor, but actually is also present when we have a system of multiple conductors, when we consider inductance only of one of them with itself, if you want. All right, so first off, if I give you this seemingly very innocent equation, which is Newton's second law, F equal ma, where m is the inertial mass of an object, a massive object. Do we question? So in this case, more than we, do you question m, the mass itself here? I don't think so. M happens to be a proportionality constant between, it's a constant in this case, of course it doesn't change with time or things like this, in which case it's more complicated, like in rockets or things like this. But in this case, it's in between the force and the acceleration, okay? It's an intrinsic property which fulfills this equation of massive objects in gravitation. So we do not question it. For some reasons, as for the case of capacitance, but even more so in the case of inductance, all students do not understand the concept of inductance. What is it? Some people say, is the object, the circuit element where the energy associated with the magnetostatic field or magnetic field in general is stored? Yeah, you can say that. Means nothing. Actually, is a fundamental property of an object, a conductor, in presence of currents, as much as the mass is a fundamental concept of gravitational objects, of inertial masses, of massive objects. So conductors with currents are characterized by an inductance, and we'll come to this in a minute. However, there is an important caveat which we need to give before starting this next discussion, which is here, after in this course, we'll consider only so-called linear materials. That is, we will not consider ferromagnets, so ferromagnetic materials, like magnets. Okay, so if you have ferromagnetic materials, or in, like for example, iron, cobalt, nickel, etc., or alloys of them that form ferromagnets or ferromagnetic materials, we will study this in Phys 342, then the consideration we're making here are a little bit more complicated. You cannot really straightforwardly make this consideration, and things can become trickier. For now, we consider that all our currents are steady currents. We have EMFs generated by steady currents, electromotive forces generated by steady currents with conductors in absence of ferromagnetic materials, okay, typically in vacuum for this course. All right, so if that is the case, what happens is that consider we have an EMF. So an EMF, an electromotive force, generates a current I. Now suppose now that it also generates a current I prime if we change somehow the power associated with this EMF. So with different powers, I have a knob. With a certain knob, I generate I crank up this knob and I generate I prime, a different current, which I can always do by changing the power of the source if you want. So suppose I do that in presence of linear materials. This means that this I prime, which is just powering more this EMF, will be proportional to I linearly by means of a coefficient k, a constant k. Since everything is linear, this also means that j prime vector will be equal to the same k times j, all scales with this k. And so A will scale with this k, and B will scale with this k, because everything here is generated by this EMF. So if the first scales in this fashion, everything scales in this fashion. Most importantly, it also happens that the flux associated with the border, with the contour gamma prime, also scales with this k. Now, from this equation here, we know that k can be rewritten as I prime over I. And so if you use this equation down here, we obtain that phi gamma prime is equal to k, which is I prime over I. So it's phi gamma. We can regroup it a little bit and say that it's phi gamma divided by I times I prime. And as it turns out, this quantity here, it's our K if you want. And so, well, it's a constant. And so it's not K, it's a constant. And this constant, we call it L. This is the inductance. I mean, all stems from the original K, but of course it's a different constant. It's not K, it's L, which is an inductance. The units of which, incidentally, are H, or Henry. This is the SI units of inductance. Okay. So now, from this, basically, what we see is that phi gamma prime divided by I prime is equal to phi gamma divided by I, which is equal to L. Okay, this is the key result of this. And this is an experimental evidence. Well, of course, everything follows from this linearity, but also experimental evidence clearly shows that if I crank up my current, the flux associated with the magnetic field due to the current, phi gamma prime, the ratio between that flux and that current I prime is the same as if I reduce the current on the same conductor, I get a different flux, the ratio is a constant, which is the self-inductance of this conductor. So this is very similar to what we had found previously in the case of the capacitance, where we had the capacitance, it was the positive charge divided by the potential difference of the positive minus negative plates, for example, of two conductors. And this one, for example, can be prime divided by prime. And then if I choose a different charge, just Q plus, and I divide it by delta V, this is equal to C, the capacitance, okay? So you see there is a one-to-one correspondence between these two concepts, if you want. And so as much as the capacitance and the mass are some intrinsic properties of conductors and massive objects respectively, in the case of capacitance, this is a property of associated with the electrostatic field, with the electric field in general, if you want, with the electric field or electric potential, the inductance associated with the current and electric flux, okay? So that's what happens. This is from experiments that what comes out. So the inductance is this fundamental property, okay? So this allows us, in general, to write phi gamma as Li. Phi is equal to Li. That's a critical result, which is super useful in all circuit applications if one day you will encounter those in your career. Okay, so now an interesting thing which is worth pointing out here is the fact that the self-inductance L is always positive. So L, no matter what, L larger than 0, always. So if you do a calculation and you find that your L is negative, unless you're doing some really complicated circuits, which I'm not going to, like parametric amplifiers, and if you find an L negative for self-inductance, you're doing something wrong. In fact, let us consider a filiform conductor here, oriented in this direction counterclockwise gamma, with current intensity in the same direction I, which is steady, a steady current here in this direction. From the right-hand rule, in this direction here, we know that the normal unit vector of this surface associated with this border gamma, of course, comes towards me because it's right-hand rule counterclockwise. This current I has the same direction as gamma. Since I is given to me by nature or by the problem, gamma, I can choose it. It's a geometrical representation, so I can choose in the same direction or not. If I choose in the same direction as I in this case, by convention, is positive. Good. So here we have a positive I, or if you want here a positive I. N, the normal unit vector, points in this direction. Here, this is my N. Right-hand rule. What about the magnetostatic field generated by I? Well, it's the ALBS law, and so it goes also right-hand rule in this fashion. So it comes towards me, so B also comes towards me, which means the flux of B through this surface, which is characterized by N, and namely the surface is this surface here. I could choose any other surface, but they are equivalent. Of course, the surface on the board, which has gamma as a border. Again, there are infinite such surfaces which would have gamma as a border. I only choose the one on the board. In this case, B and N, when I do the flux, are the same direction, so the flux is positive. So phi is positive, phi gamma is positive. So in this case, phi gamma is positive. The current is positive. The ratio between these two clearly positive. What happens if I choose on purpose, so let's resketch it down here, the second case. Okay, this is my I, points of course given by the problem as always in this direction, this is my I, but I choose to make my life harder if you want, and I can always do gamma pointing in the clockwise direction. So in this case, since I points opposite to gamma, the sign of I is negative. Similarly, the n associated with this surface here now points inward. So it's like this. This is n. What about b? B still points towards me, because right-hand rule for ALBS equation. So we have in this case, clearly, n negative flux because n and b point in the opposite direction of each other. So the flux with this new convention on gamma is negative for this specific gamma here. The current is also negative in this convention. And the final result is that L remains still positive, no matter what. So in both these cases, 1 and 2, the inductance remains positive, okay, which is an important property. So to summarize this video about self-inductance, for self-inductance we consider only a single conductor if you want. First of all, I wanted to make sure that we don't question the concept of mass, which is similar to the concept of inductance. Inductance is for conductors with a current, and mass is for massive objects. Capacitance is for conductors with electric fields. Okay. We consider linear materials, that is not ferromagnets. We have an EMF which we can power up or down, generated currents I or I prime, where I prime, let's say, is larger than I, or smaller, it depends. Then K is positive, is larger or smaller than 1. And this I prime is proportional to I by means of this K. Since everything is linear, all these relationships fulfill, so we can reshape them in this way, where this is my inductance constant. And so this is what the experiment tells us, that the ratio of the flux associated with a certain current is always a constant self-inductance, similar to the concept of capacitance. Henry are the units, phi is equal to I, and L is always positive, and we have done 2 cases where we have shown that it's always positive. That's it.